top is 1, and then carefully on the bottom, what is the derivative of e to the negative t? Negative e to the negative t. Now we're supposed to take a limit again, right? Yeah, so here's what I would do. Like, maybe if I'm kind of confused about this, what I would do maybe is bring this e back up. Like it's negative down here, right? Let's just bring it back up. So wouldn't this be negative e to the t? So that's a negative, like a negative 1 that I could bring out front. And then e to the negative t on the bottom, I can just pop it up as an e to the t. And now let t go to negative infinity again. So look at the graph of this and head out to the left. And it goes to 0, doesn't it? So this thing goes to 0. So that limit is 0. OK, so this goes to 0 and this goes to 0, which means that that piece right there heads to 0. Yes? OK, all of that work there. So one of the biggest, I guess, things that I take points off on a test are when a student goes from this step to saying that that's 0 with no work. They just say, oh, that's 0. And they don't justify it at all. Okay? You need that step on these problems. All right? You have to show how you're concluding that thing actually heads to where it's going. So I want to see this, L'Hopital, whatever it is you do. All right? We're not done, no? Right? No. OK, so we had negative 1 here, minus 0. That was that. And then plus, now we need another limit, don't we? OK, let's see what this limit does. This limit might be a little different, so let's look at it. We have the limit as r goes to infinity of r e to the r minus e to the r. Right? That's our issue here. Now we're going to positive infinity. So where does this go? Infinity times, now what does the e function do as you let r get big? So that means what does the e function do as we move to the right? Gets bigger. So it's infinity here, right? Not 0. So that's not a problem, is it? Infinity times infinity is infinity. But here's the problem. Minus infinity. So infinity minus infinity is not 0. Okay? It's like you've got a huge number. You don't know how big it is, but it's huge. And you're subtracting another huge number. So you don't know which one of them was huger. You like that word? Huger? Huger-er. More huger-er, right? So you still have to resolve this. So the standard practice when you see infinity minus infinity is to factor. So you look at this expression, you see, can you factor anything out? And James, you had mentioned this earlier. We could have done this earlier too, but I didn't, just to show it could be done without factoring. E to the r comes out of both, right? And what are you left with? R minus 1. So pull e to the r out of both of those. And now just run your limit again. Okay, so what happens here? R goes to infinity, e to the r goes to infinity, times, now what's infinity take away 1? Still infinity, but now you have multiplication, don't you? Multiplication of infinities is infinite. And what does this mean? This thing goes to infinity, right? Minus, minus, plus 1. So here's where we are. This is negative 1 plus infinity plus 1. So it's infinite, right? It diverges. The area under that curve becomes infinite. Maybe we should look at it. Let's go back to Desmos. It was x times exponential of x. Was that it? It was x e to the x, right? So hopefully you can see here from this graph. I think the graph is very telling here, isn't it? And look at what it's doing. Look what it's doing to the right of 0, right? It's like taken off. So the area underneath it is becoming unbounded. And we see that right here in this piece. Yeah? Let me ask you this. What's that? -1. So instead of going from negative infinity to infinity, what if we just went from negative infinity to 0? Off the graph, it's just now looking from here over, right? Yes. Do y'all see that? It's asymptotic towards the x-axis. This area is -1. It's counting it negative because it's below the x-axis. Which reminds me, remember last class I thought there was a problem with my code? Do y'all remember that? Yeah, maybe you do. See if I can. It was this one over here. It was that, I think, yeah, it was right there. Do y'all remember that? I was like, what the hell's wrong with my code, man? I'm so pissed off. I was like, that should be giving you a negative answer, I think. Do y'all remember that or not? Yeah. It's actually correct. This is correct because what you're doing is you're taking one endpoint and subtracting the other. So this endpoint has a value of -1 and this endpoint has a value of 1, but you're doing that minus that. So it's -1 take away 1, so you get -2 here. Right endpoint minus left endpoint. And so that negative area corresponds to -2. I know why. Last week I was somewhere else last week. So I apologize. I should have realized that when I was looking at it, but it was correct. All right, what do y'all think? Yeah? So L'Hopital is going to come into play, all right? All right, so one example of a real application of these improper integrals is actually, yeah, that's your standard normal distribution from statistics, if you've taken a stats class. Has to do with, well, normal distributions and in this formula that looks crazy. Let me rewrite it so it looks a little bit cleaner. It's 1 over 2 sigma pi e to the negative x minus mu squared over 2 sigma squared. So when you look at that, this is a function. It's an exponential function. And here, sigma and mu are both constants. And then so is pi, obviously, in 2. So the only variable here is x. So in statistics, mu is your mean, your average, and sigma is your standard deviation. So if you know your average and your standard deviation, then the graph of this function gives you what we call our standard normal distribution, and it looks something like this. Okay, looks something like this. Your bell curve. And if you change your value of the mean, you can move your average wherever you want. So let's say we're talking about the average heights of human beings, right? Then our average should be somewhere, and let's say we're measuring in feet. What do you think the average height of a human is? I don't know. 5'9". 5 something, right? Let's just go with that, right? Then you see how you can tell 5 foot something, that's our average. Most people are around this height. And then you also would have to compute your standard deviation. So if you have a small standard deviation, then you have people who really are close to that average height, or you could have a large standard deviation, which means there's a very big spread of heights. Now, this graph is not good for heights of people. Why? Why is this graph not good for heights of people? If the x-axis is the height of people, then we don't have negative heights, right? So standard normal distribution is not good for talking about heights of human beings. What you would need is a graph that starts here at 0, goes up, comes back down, and then goes like that, and goes forever. That's what you would need, and that's a different type of distribution. Yes?
I was going to say you have to turn it into a z-score to do that.
A what?
You would do it like how we would do it in stats, is we take all that value and then turn it into z-scores.
Yeah, but you know what a z-score is? All a z-score is, it's an area. But in stats class, a non-calculus-based stats class, you don't know how this corresponds to integration. So you go off a table. They tell you, okay, look, if you go out to this z-score, or whatever it is, then a table will tell you how much area is over here, right? And then you can also deduce how much area is this way, because it's always going to be 1 minus that. But the whole idea behind this is that the total area the total area under this standard normal distribution, the total area is 1, always. And so that's why the z-score works. I don't know if that makes any sense. Yeah.
So is the z-score like the maximum or the minimum of like let's say the tallest person in the world or the shortest person in the world?
No, you would say this. Let's say that we have the average height of human beings is 5'8", let's just say.
Yeah.
And we have a standard deviation of 4 inches, whatever that is, right? Then you say, okay, what if you have somebody who's 7'2"? You can calculate what's called their z-score, okay, which means you can find out where on this curve how far out they are, and you could figure out the probability that a person would have that height. So you'd say, look, maybe with the 7'1", maybe you're out here where this area out here is like 0.02.
Okay.
Okay, and which means that this area over here would have to be 0.98 because it adds up to 1, which means that they're in the top 2%.
Yeah.
I think 7'1", though, I think you're going to be further out. But this is, I'm getting too much into stats. I don't want to talk z-scores. What I want you to get from this is that improper integrals come into play when you want to talk about what are called probability distributions. And what we need for probability distributions is that the area underneath the curve in both directions forever must be 1. And it's tied to this concept. We need the area to be 1. The concept comes from this. And the simplest example I can give you is this. If we take a standard die, right? A die that you roll, you know, it's got 1, then it's got 2, right over, right? You've got your die. Okay, we can talk about the probability of rolling a certain number, right? So what we could do here is we could say on this axis, this is the outcome. And then right here we could say, what's the probability of that outcome? So let's break it up like this. This is 1, 2, 3, 4, 5, and a 6, okay, outcome. So what is the probability that you're going to roll a 1? 1 out of 6, right? So if this is 1, 1/6 would be right here, right?
Yes, sir.
And then what's the probability of rolling a 2? 1/6. 3, 1/6. 4, 1/6. 5, 1/6. 6, 1/6, right? Now, what is the sum of the area of that picture? 1, right? How wide is this? We can say it's 1 unit, 1 unit, 1 unit, and how tall? 1/6. So the area of this is 1/6, 1/6, 1/6, 1/6, 1/6, 1/6. So when you take the sum of all of the probabilities, right, together, it should be 1. There's no other outcome. You can't roll a 7, right? So if 7 out here, there's a 0 probability. A 0, there's no negatives, no possibility. It could only be these finite values, 1, 2, 3, 4, 5, 6. Yes? Okay. So all probability distributions have to have a sum, the sum of the probabilities for all of the events together, all of the possible outcomes have to sum to be 1, which is 100% probability that one of these is going to happen, right? Okay, now these types of variables, like rolling a dice, rolling a die? Die, whatever. This is called discrete random variables because they can only take on values that are integers. So like you roll a die, boom, that's 1, 2, 3, 4, 5, 6. But there are other types of variables out there that are not discrete. For example, that soda can right there, or whatever that is in there. How many ounces does that say it has?
16.
16 ounces. So let's say we had a perfect instrument that could measure how many ounces are in that, like as accurate as we ever want. Okay, and let's say we get a case of those and we start opening them up and measuring them. Do you think each one of them is going to be dead on 16 ounces? No. So you're going to have something like this. 0, 16 ounces, and then you're going to have something like, okay, what's the probability that you're going to have 16 ounces dead on, dead on? Well, maybe decent. Yeah, you might argue not much. I mean, that it's 0, but you could argue that for any specific value, it would be nearly impossible to get that value, wouldn't it? But let's say we do a little range, a little window here. 16 plus or minus a certain window. Would you say that's a pretty good probability?
Yes.
Not 100%, right? But pretty good? Maybe like, I don't know, 80%? 0.8? Now, as you move away and start getting closer to like 17 ounces, 18 ounces, probability is going to drop, isn't it? So this is going to start doing this. And then, can you say that it won't be 20? Yeah, maybe you can, maybe you can't.
Well, you'd have to take the dimensions of the can.
Yeah, the dimensions of the can might limit you. But the idea is still this, that you have the probabilities in the middle, right? Then you have a little like window and then everything starts to drop off. What you want is that the sum of the area under this whole thing, right? You want that sum of that area to be 1. And then what you have is a probability distribution. Make sense?
Yes.
And the only way you can talk about, these are called continuous random variables, like measuring the liquid in something as opposed to the dye. The dye is discrete, takes on finite values. Measuring the liquid is a continuous variable. The only way you can ever do any statistical work on continuous random variables is if you can find areas under curves, which means you have to have integration. Yeah? Okay, so I want to go back to this problem we did a second ago. Would that be an example of a probability distribution? Why not? It's not equal to 1. Okay, how could you fix it and make it equal to 1? You could change the interval, but the whole idea is that you want it to go in both directions forever. You can't, I'm going to tell you, you can't change that. Okay, multiply by something, but not 2. What is the answer to this?
Pi.
What do you want it to be?
So you do it, multiply it by pi.
Yeah, just multiply it by 1 over pi, or just, if you like, just do this. 1 over pi. I know that seems ridiculous, but that's true. So if you do 1 over pi times that integral, you get 1. And that would be a probability distribution, because that means the sum of all probabilities is 1. Yes?
Is that how like percentile works? Like gradient percentile?
Yeah, when you're in percentile, I mean, it's pretty much the same thing. Now, if we go back to that thing we just had, right? I don't want to write it down again. If we go back to this example right here, the standard normal distribution, what I want you all to see here is that this right here, this 1 over the square root of 2 sigma pi, is kind of like the 1 over pi is here. It's what we had to scale it by in order to get it to be 1. And then the rest of it is the function itself. And I'll tell you right now that this function right there, we cannot integrate with any methods we have. Okay? We don't have a method to integrate that. That you would have to use series for. Alrighty, we're moving on. We're still in type 1. There's one last example here. All right, this will show up later. This will show up again in chapter 8. All right, this says, show that the integral from 1 to infinity of 1 over x to the p dx is divergent if p is less than or equal to 1 and convergent if p is greater than 1. All right, so let's first talk. This is a type 1, isn't it? This is type 1. Do we have any issues on the interval 1 to infinity? Do we have any issues with the function itself on this interval? Is there anywhere where this function is not defined? No. Only at 0, right? And that 0 is not in there? So this is type 1. So I'm going to just do what we've been doing. I'm going to say this is equal to the limit as t goes to infinity of the integral from 1 to t of 1 over x to the p dx. All right, just convert it over from the improper integral into the limit version. And now I need an antiderivative, right? I need an antiderivative. So I'll do that on the side. What's the antiderivative of x to the negative p. So all I've done here is I've brought the x up out of the denominator up into the numerator so I can use the power rule. Right? So using the power rule, what is this? The antiderivative. This should be 1 over. So whatever that power is, what am I going to do to it? Add 1. So negative p plus 1. And then it's going to be x raised to the negative p plus 1. Would you all agree that that's the antiderivative? Is this always valid? There is a value of p where this doesn't work. If p is 1, right? So please recall that we're going to have to come back and think about what if p is 1. So this is true if p is not equal to 1. That way we don't get division by 0. All right. Okay, let's come back over here. We're going to do the limit as t goes to infinity of the antiderivative, which was 1 over negative p plus 1, x to the negative p plus 1. And we're evaluating that where? 1 to t, right? Y'all okay with that? Okay, y'all ready to plug in t and plug in 1? Limit t goes to infinity, bracket, parenthesis, parenthesis, close bracket. Okay, we're going to plug t in first. T is going to go in for what variable? For x. We're replacing x with t. Okay, so this becomes 1 over negative p plus 1, t to the negative p plus 1. And then we're going to plug 1 in, right? For x, which is 1 over negative p plus 1, and then 1 raised to negative p plus 1. Yeah? Let's talk about this one first. This is 1, right? It's not getting close to 1. This is 1. And so what's 1 raised to any power? 1. Okay, so this is 1 and then times that, right? So over here on the side we have minus, and then we have 1 over negative p plus 1. And that is a number, right? That is a number. As long as p is not 1, then this is a number, right? The question still remains, what about this? So we have to let t go to infinity, right? So remember at the beginning of class I said I'm going to do this and then later on we're going to come back to it? And that way I don't have to spend 10 minutes doing it, right? So I'm there. So go back and look in your notes from earlier. What did we say? We said if we have the limit as t went to infinity and I went t to the n, right? What did we say about this? It converged when? If n was less than or equal to 0, right? It converged. And it diverged when? When n was greater than 0. Okay, do y'all see that this is exactly what we have here? I'm taking the limit as t goes to infinity, right? And I'm doing, just ignore this, okay? Ignore that. And just look at this piece. Isn't that like t to the n? But it's negative p plus 1. So if n is the power up there, then what do I need for convergence? I need the power that's up there to be what? Less than or equal to 1? So this will converge. How do I say this? I guess I'll go, I'm running out of room, damn it. Okay, I don't want to do anything up there yet. So using this idea on this piece up here, that piece right there will converge if what? Converge if the power up top is less than or equal to 0. Well, what's the power up top? If negative p plus 1 is less than or equal to 0. Now, solve that. Move the p to the other side. Add p to both sides, and what do you get? 1 is less than or equal to p, or p is greater than or equal to 1, right? So this piece right here will converge so long as p is bigger than or equal to 1. And if that converges, and this is a number, then the whole thing converges, doesn't it? So haven't we shown that, hold on, shit. What happened? Was it backwards? Is this backwards? No? Oh, I know what the issue is. Yes.
If you think that p is equals to 1, wouldn't that make that undefined?
No. P is not 1.
So maybe we can.
No, but we can, if P is 1, okay? If P is 1 here, do you all agree that if P is 1, this is 1 over x? And the antiderivative, that's just natural log of x. So we'd have a different antiderivative to work with. Yes?
Yes.
Okay. But this right here, it converges if n is less than or... Wait, was this 1 or 0? Hold on, go back to this. It was 0?
Yeah, that's correct.
Okay, so if it's bigger...
So we have the one that converged to 1 and one that converged to 0.
Yeah, but they both converged, right?
Yeah, but it's going to converge if it's greater than 1, because then that will give you a negative exponent, which would be less than 0. So if you have t is
P
equal
is bigger than 1.
t power of n, if n is less than 0, then it diverges. But if the way we rearranged our equation, it's p is,
Was this what we wrote down earlier?
yeah.
It is, right? Hold on.
The n is still less than 0 if t is greater than 1, which is negative.
I did do t diverged. If it was greater than 0, this diverges. No, I'm not listening to you. Sorry, hold on. No, I will listen to you, but hold on. Let me first just get my bearings here for a second. Okay, so this is what we had written down, right? And this is true. If that goes to infinity, that's bigger than 0. This thing should blow up. If it is 0, it's going to converge. If it's less than 0, then it drops down. That blows up. That goes to 0. Okay, so that should be true. Now, what are you saying?
I was saying n less than or equal to 0 is the same as saying p is greater than or equal to 1, because if you plug
Exactly.
1 or greater than,
But it's not equal.
n will equal 0 or be less than 0.
Yeah, but look at what this is saying. Is that 1 over x is p? I think. No, that's right. So this from this statement, this is true, right? P is greater than or equal to 1.
Yes.
Okay. So p is greater than or equal to 1. We're trying to show that if
We're going to have a greater negative.
Okay. I almost made it through the day without being an idiot, but I still am, unfortunately. What is this saying here?
What is less than?
Okay, so let's take out the equals 1, okay, because we omitted this from here. Okay.
Sir,
Yes.
isn't this sign going to change because you're dividing by negative?
I added p to both sides.
Oh.
I added p to both sides. So if you divide, you'd have to move the 1 over, it'd become negative, then you divide, then it would flip and you'd still get the same. Okay. Because we eliminated 1 as being here to begin with, we are going to use this. This right here will converge so long as this is not less than or equal to 0, but just less than 0, right? Which means that p has to be bigger than 1 for convergence, which shows this. Yes? P is bigger than 1 for convergence. Now, what if that power right there is greater than, what if this power right here will have divergence if that power negative p plus 1 is greater than 0, right? Move the p over, that means 1 is greater than p, so p is less than 1. That's this, right? But what about the equals 1? So that we have to revisit now. Okay, it was right the whole time. I just, for some reason, when I looked up here, I saw those backwards. Because I think it's because of the way I wrote it. But are y'all following? Okay, so convergence so long as p is bigger than 1, we've shown that. Divergence if p is less than 1, we've shown that. We just need to see where that equals comes from. So go back to this point right here, and let's just say what would happen if p is 1. If p is 1, we have integral x to the negative 1 dx, which is integral of 1 over x dx. And what's the antiderivative of that? Natural log. Okay? And so what's going to happen in here is you're going to have natural log. And what will happen as t goes to infinity? What happens when you plug infinity into natural log? It becomes infinite, right? So you're going to get divergence. So I won't work through this, but if you work through it on your own, set up your limit again, you'll get divergence. And that's why if it's this equal to 1, we get divergence. Yes?
So would you recommend that if it says show that that's divergent, then break it up into its different equalities?
Well, I am not going to ask you to show this ever, all right? I just want you to be able to use this now, all right? This is the way you'd show it, and then now we use it. So if we do this, okay, so this is kind of the end of it all here, is now if we do this problem. Does that diverge or converge? So does it look like this? Is that 1 over x to a power? What's the power on x? 1/2. Does that converge or diverge? It diverges because the power is 1/2 and 1/2 is less than 1. So this diverges. Okay, without us showing any work. See, we've generalized, and now we can do this for any. So this is divergent, right? Because p is 1/2. What about this? What is that? Does that converge or diverge? Converges. It converges because what is the power on x? 4/3. And 4/3 is bigger than 1. Now, does this tell us what it converges to? No. We just know it converges. Got it? Converges. P is 2, right? Yeah. Has to be 1 to infinity. Yep. But this is a good question though. What do y'all think? So if from 1 to infinity converged, right? That means the answer was finite. The area from 1 to infinity was finite. Then the area from 2 to infinity should be finite also, right? Because all you're doing, you're taking less of the area, aren't you? So it should be finite. You're taking a finite amount less than this. Pardon? It's not the same, it's just convergent. Yeah, so this converges. It's just not the same area. How about this? What if we do, where's a divergent one? What if we do this? (20 to infinity) of a divergent one. Do you think it still diverges? Yeah, because the way you look at this is as follows. We know that if you go from 1, right? We know if you go from 1 to infinity, it diverges, which means this thing becomes infinite, doesn't it? So if you, instead of start at 1, you start at 20 and just go from here to here, well, this is still just a finite amount of area, isn't it? This is finite. And so we know that the rest of the way is infinite, right? Like the whole thing's infinite, and if you take out this finite part, it's still infinite. So changing that 1 to some other number doesn't really, bigger number, to the right of 1, doesn't make a difference. Now, do you think this makes a difference? 0 to infinity? Absolutely makes a huge difference, because now what you have is you've included 0. And 0 can't be plugged in here. So this is a type 2 and a type 1 at the same time. Right? You've got an infinite interval, But within that interval, you also have a discontinuity, which we haven't talked about yet, all right? So we'll have to continue with type 2s later. Yeah, I think that's a good place to stop. Would you say? Make sure there's nothing else here. Yeah. Okay, so the exam is on Thursday. There is a chance, there's a possibility that I'll only be here for the first 45 minutes of the test. I have something I'm going to try and be at 2:30 on Thursday. So I might have a proctor come in after about half an hour of starting the test and finish off the test in here. So that may happen, just FYI. And if that does, don't cheat. Because when a proctor catches you, that's like even worse than me catching you. So do your own work, all right? And as far as preparing for the test, you're allowed to have your formula sheets, right? Just everything I've provided. Yeah, I mean, I don't think there's any restrictions on what I've provided you. Just don't edit them. Don't write your own little formulas unless I've told you you can. Study the main parts of this. I showed you last week, a sample test, right? So main things, like I haven't written the exam, so main things I'm thinking about are like trig sub, right? Trig sub is a big deal. I'd like to test you on more than one type of trig sub, right? I'd like to see that you can do like an A sine theta. I'd also like to see that you can do an A tan theta or something like that, or an A secant theta. I'm pretty sure there's going to be something where you have to complete the square, right? Like one of the integrals we had was where you just have something like this. I'm just making this up on the fly here. That's the type of integral where you can't do anything until you complete the square. And maybe even we throw a number out here, so you have to factor a number out first. That one might actually work by factoring. But, and then what would happen if you put an x up there instead? Like, is that basic U sub or is it not? So, I mean, completing the square will be there somewhere. And then partial fractions, right? So you'll have to use long division on at least one problem. So always make sure you're looking for that. Is the degree of the numerator bigger than the denominator? Don't miss that step, right? If you miss the long division step, it's going to be wrong after that. Right? For every distinct linear factor, you have A over that, B over the next one. If you have an irreducible quadratic, you have to put something like BXC over the irreducible quadratic. What else? Okay, so improper integrals, right? So it would not be surprising, it should not be surprising for you to see an integration by parts in there for one of the improper integrals. And if you don't see one, don't be surprised either. Okay, so I mean, I'm just saying integration by parts is on the table, but for one of the improper integrals is where it would be. Only type 1, no type 2s. And so within those type 1s, you're going to have some L'Hopital. It's going to show up when you do your homework. I think it shows up in the homework, so it'll show up there. Yeah. So studying, I don't know. I was asked about studying, just try and get some random problems, sit down and give yourself that testing environment. Maybe have a study group, get together and throw problems at one another. I have a couple of textbooks down in my office. You're welcome to come by after class if you want to just like take a picture of some problems out of that book or something. I can, whatever. Any questions or concerns or anything before we call it a day? Sure.
Is so at the end of chapter 6, there's the how there's kind of that review of the whole
The chapter review, yeah.
Yeah. Is would you say that's a pretty good?
Well, the problem with the chapter review is that there's sections in this chapter we didn't cover.
Yeah.
So unless you know what is what in the chapter review, it's going to be maybe hard. I can tell you right now. Let's see. I still have time. So in the chapter, no, I'll just call it out. Like if you were looking at the chapter review, where the hell? You have to remember the chapter review includes like
Yeah.
integration by parts. It has everything, right? So just by looking at this right now, the things that I can see that are going to be trig sub or partial fractions are problems like this is page 363. Number 11, number 14, number 13. So 13 and 14 are, I'm not even going to tell you what they are.
Okay.
18, 19, 21. Oh, number 8 also. I didn't see number 8 up there. Number 25 looks pretty intimidating. $33. Okay, and then after that, 41, 42, 43, 49, and 50. Those are all improper integrals. Out of the chapter review, I think those are good problems. And some of those are definite integrals.
Okay.
So it might be a trig sub, but then you have to, at the end, plug in the numbers.
Yeah.
Yeah. Yeah. From the chapter review, that kind of narrows the focus down there for you.
Okay. Thanks. Appreciate
Yeah,
it.
no problem. Yeah, but don't limit yourself just to that. Yeah, I mean,
Yeah.
it's just out of the chapter review, those are problems that apply to this exam.
Yeah, I'm gonna do more practice than just like the chapter.
Yeah. All right, everyone. Have a good one.
So, you know how you said that this converges because it was greater than 1? Why can't we just rewrite it like that?
Well, in the way that we started it all out, we said, okay, what if we have 1 over x to the p, right, dx? So in the way we started the problem, we said, look, we're always going to treat p as the power on x as it sits in the denominator.
Oh, okay.
So when you look at this thing, cube root of x to the 4th, you have to rewrite that as 1 over x to the 4/3, and that's when you're looking at what p is. If you bring it up, then of course it's going to change it to a negative, but then it doesn't look like this.
Okay, so we have to keep it in
Keep it on the bottom in that form to be able to identify p.
Oh, okay.
Yeah.
Okay, that makes a lot of
Okay? Uh-huh.
Did the DSS office, did they send that letter of accommodations?
Did you do it at the last test?
Yeah.
I think they did. We just didn't have it in time for the first one, right? But
Yeah.
didn't you go over there or no? Did you not?
I went over there before the test. I went over there.
I just want to turn my camera off, okay?